25 degrees.
Okay.
So 25 is what in Celsius?
Fine.
-4.
-4.
-4. And snow is expected today. And snow is also expected today, so it's going to be a challenge.
ഇതൊന്നും കണ്ടിട്ടുണ്ടാവില്ലല്ലോ മറ്റേ പണ്ടത്തെ
Krishna sir.
Yeah.
Yes, sir. Yes. Yes, ma'am.
Can you mute everybody?
Yes.
എന്താ അല്ല നമ്മുടെ അതായിരുന്നു ആദ്യത്തെ അതിന് മുന്നേ കാരണം നമുക്ക് ടി വിയിൽ ഉണ്ടായിരുന്നു. നമുക്ക് ഒരെണ്ണുണ്ടായി സ്വിച്ച് പോലത്തെ ഒന്നും ഉണ്ടായിരുന്നു ചാനൽ മാറ്റാൻ.
So can you make me co-host? Then I can share my screen.
Sir, you can share your screen. No need to make it co-host. I have share here. Multiple participants can share that simultaneously.
Oh, okay. That sounds good. All right. Okay, whenever you're ready, I'm ready.
Yes. Ma'am, shall I start?
Yes, you can start.
A very good evening and welcome to the third day of FDP. Today we are honored to have Professor Krishna Reddy and Professor JLS Babu leading to the session. We are delighted to welcome Professor Krishna Reddy from Illinois Institute of Technology, Chicago, and from GLS Babu from ISC Bangalore for today's insight session. Professor Krishna Reddy is a globally recognized expert in geotechnical and geo-environmental engineering, specializing in sustainable construction, waste management, environmental remediation. His session will provide the valuable insight into the cutting-edge research innovative solution for sustainable infrastructures. And whereas Professor JLS Babu, a distinguished faculty members from ISC Bangalore, has made a significant contribution to the geotechnical engineering with expertise in soil enforcement and ground improvement techniques and geosynthesis. His talk will reach the theoretical advancement and practical application, offering a comprehensive understanding of modern geotechnical solution. We look forward to enriching the discussion and valuable knowledge sharing from both the esteemed speaker. May I now invite our esteemed Pro Vice Chancellor, Professor G. Sridevi, to share a few words about Professor Krishna Reddy. Ma'am, please.
You're muted, Sridevi.
Am I audible?
Yes.
Yeah.
Yeah. Thank you, Dr. Krishna. Good evening, everyone. It's my honor to introduce Professor Krishna Reddy, sir, a renowned figure in the field of civil and environmental engineering. Sir needs no introduction, but since this pleasant duty is given to me, I'm taking this honor of introducing him. He is a distinguished academic and researcher in the Department of Civil Materials and Environmental Engineering at the University of Illinois, Chicago. He serves as the director of both Geotechnical and Geo-environmental Engineering Laboratory and Sustainable Engineering Research Laboratory at the university. With over 30 years of experience in civil geotechnical engineering, materials, and environmental engineering, Dr. Krishna Reddy has significantly contributed to the fields of sustainability, resiliency, infrastructure, water, energy, and environment. Now, we have all witnessed how diligently sir was working during the COVID time. During COVID pandemic, Professor Krishna Reddy sir has demonstrated exceptional commitment to the education by hosting a series of webinars over a wide range of topics like site remediation, waste management, sustainability, resiliency. And these sessions have provided valuable insights into the geotechnical, geo-environmental engineering, benefiting both students and professionals alike. His dedication to advancing geo-environmental engineering has been instrumental in introducing and popularizing this field among engineering students as well as researchers. Professor Reddy's extensive research, innovative teaching methods, and proactive engagement during challenging times have solidified reputation as a leading figure in the civil and environmental engineering. And sir also shared me all his UG course lectures. Sir, they are very, very engaging, and I myself has enriched a lot. The examples you were taking during your lectures are phenomenal. Sir has been widely recognized, earning him prestigious awards like Leonard's Lecture at Purdue Geotechnical Society, Purdue University, Fulbright Academic and Professional Excellence Award, then Wesley Honor Award given by Environmental and Water Resources Institute, American Society of Civil Engineering, and University Scholars Award by University of Illinois, Award of Excellence in Teaching by University of Illinois. And the list goes on. Because of paucity of time, I'm not giving the entire list. Sir, really, we are honored to have you for this FDP program. And I'm sure your lecture is going to benefit students, faculty, and researchers alike. Over to you, sir. Thank you very much for accepting our invitation.
Yeah, thank you so much for that introduction, Professor Sridevi. So let's see if you can see the screen properly.
Yes, yes.
Yes, sir. Make it
Now,
slides from yes. Right now it's okay, sir.
yes,
Okay, you
we can
see
see.
only one screen, right? Okay.
Yes.
All right. So yeah, thank you so much. Did I mess it up? It's good, right? Just I don't know.
Yes, sir. Yes.
Yes, it's good.
All right. So let me just stop 1 second. It has something happened. All right, it's good, right?
Yes, that's very good.
Okay. All right. So yeah, good morning from Chicago. Good evening, everyone in India. So I'm sure you're enjoying warm weather there, but here it's very cold. As I was telling, -4 degrees, and we are expecting a lot of snow. But I'm looking forward to visiting India next week. So hopefully I can enjoy all the good weather that is going on in India.
Oh,
Yeah,
thank you.
I'm very thankful to Professor Sridevi. I have known her for a long time. I visited her previous college, and also she has been very active in Indian Geotechnical Society. I met her many times at Indian Geotechnical conferences. So I am so happy to see this FDP program on a very important topic, application of geotechnical engineering for the development of sustainable and resilient infrastructure, which is extremely important topic under current scenario. So I congratulate the program committee for taking up this topic and organizing this FDP. And I hope all the participants are going to be benefited by this program. I'm thankful to be invited. So I'm going to share some of my perspectives on sustainable and resilient infrastructure and role of geotechnical and geoenvironmental engineering. I am a geotechnical engineer, but I do much more than traditional geotechnical, so geoenvironmental. So you can see how geoenvironmental engineering can be applied towards a sustainable and resilient civil infrastructure. So I'm going to be a little bit more general, give you broader overview on this topic. But if you want to go into details, you can contact me later, or you can pursue on your own as we go into the future. So what I'm planning to do is just to give you some definitions of terminology. A lot of people use sustainability and resiliency. These are the buzzwords. You can see them used in every field, and whether somebody understands them or not, but they make whatever you are doing more attractive. So people start using these things, but I'm going to explain from my perspective what these mean. And then if you understand that one, you can see what sustainable and resilient infrastructure should be. And then I'm going to just briefly mention about what are the general considerations for a sustainable and resilient infrastructure design. And then I'm going to focus on how geoenvironmental engineering can be applied towards sustainability and resiliency and making the infrastructure, okay? So basically, I will explain very briefly what is geoenvironmental engineering is, and then I will give you several examples of how geoenvironmental engineering can be applied towards the sustainable and resilient infrastructure. And then, I have a brief closing comment. So this is the agenda. So the sustainability, what is the definition of the sustainability? So in one of my papers, I have given, more than a dozen definitions of what sustainability is. And you can find, many more than that. But the one that people use commonly is this definition. So I think everybody knows about this. Everybody knows about this definition. Very general, meeting the needs of the present without compromising the ability of future generations to meet their own needs, which is very, brief, succinct, and very powerful. But it does not really tell what to be done in order to achieve this one. So what I did is I added the last part that I underlined. So you can achieve that one. Basically, you can meet the needs of the current generation without compromising the needs of the future generations, while ensuring a balance between environmental care, societal well-being, and economic growth. So, in order to accomplish that broader goal, you need to balance these three aspects: environment, society, and economic. And this is popularly known as triple bottom line. I'm sure you have seen the Venn diagram that shows all these three elements and basically optimizing the positives of all these three elements. So why are we, so concerned about sustainability these days than before? So we have all these issues: natural resource depletion, growing environmental pollution, increasing population, increasing waste generation, increasing greenhouse gases, declining ecosystems, loss of biodiversity, social injustice, and urban sprawl, and many more. And all these things are getting worse and worse, as the time passes. So we cannot have this situation to continue. So that's why, conditions for current generations are becoming difficult, and definitely it's going to be a very problematic situation for future generation. So that's where, the concept of sustainability comes into picture, and UN has developed sustainable development goals. They said, hey, we need to address these issues, and we should be aiming to do something. And they specify these 17 goals, and they have specific targets under each goal. And you can monitor country-wise how these targets are being achieved. Okay, so this gives us some good framework at a global level on what can be done towards the sustainability and reverse the problems that we have been having. So quantifying the sustainability is very important, because you just don't want to say, whatever I'm doing is sustainable. So in order to quantify sustainability, you need to have indicators that represents those three dimensions, as I meant, environmental, economic, and social. And you need to be able to calculate those indicators, we call metrics. For environmental impact metrics, you can use the methods such as carbon footprint analyzer or life cycle assessment or other tools like that. And the problem is calculating the social and economic impacts and quantifying them. You can identify what could be those issues, but how do you quantify them becomes a challenging thing. So our research, or my research, is aimed at developing the frameworks and identifying the indicators, identifying the metrics, and how you combine all of them to call so-called sustainability index. So that's, I'm not going to talk about that one, but you can look at my papers that shows the framework and how you quantify the sustainability. So let's look at the another buzzword that people use is resilience, right? So again, there are many definitions for resilience. Again, the paper that I mentioned, it has more than a dozen definitions. But in being in civil engineering, we look at ASCE, and the ASCE has given this definition: the ability to plan, prepare for, mitigate, and adapt to changing conditions from hazards to enable rapid recovery of physical, social, economic, and ecological infrastructure. So what it means is, the main thing is, changing conditions from hazards, and addressing the issues, and mitigating those issues and adapting to those issues. There is another reputed agency in the US that's called National Research Council, and they have given a little bit brief definition: the ability to prepare and plan for, absorb, recover from, and more successfully adapt to adverse events. So again, so the buzzword here is adverse events. The main word here is adverse events. So when the adverse events happen, then you want to be, you don't want to have a catastrophe and loss of life, loss of property. You want to be able to recover from that and successfully adapt if, any such situations happen again in the future. Again, these definitions are good, but how do we accomplish these things? So you can see a modified definition that we defined in one of our recent papers is: the resiliency is the capacity of a system to prepare for and overcome unexpected crises and adapt to turbulent changes. So, whatever these adverse events, changing conditions that we are talking about, they're not well defined. They're unexpected, so when you don't expect, then it's very hard to deal with those unexpected situations, right? But anyway, those things are happening. And how do we adapt to those turbulent changes? And the idea is we want to minimize the possible impact on the environment, social, and economic factors. So whatever the system that you are working on, and that should cope up with the unexpected crisis or unexpected adverse events. But at the same time, we want to make sure that these environmental, social, and economic impacts are considered. So just like sustainability, why are we concerned about resiliency? So I'm talking about changing conditions. So the changing conditions or adverse events could be anything. It could be, economic, sudden economic, disaster, or it could be, drastic political, situation, or, more commonly, engineers are talking about changing climate. And as you see, the climate impacts that you can see, some places is extremely dry, some places extremely cold, and you have a lot of hurricanes, a lot of tornadoes, all these things are happening. Sea level rise, increased surge, all these things are contributed to climate change. And this climate change and extreme weather events are observed everywhere on the planet. And those are creating havoc in many situations, right? So in US right now, the entire California area is burning. We have a lot of wildfires. That's become a very big problem. And a lot of places, extreme flooding that is happening, and a lot of hurricanes, more than usual, and they are causing a lot of damage. And all this excess, rain, precipitation, storm events, they're causing all kinds of geohazards and consequent damages. So again, you don't let these things happen, have all the impacts to the people and to the surrounding environment. So these things are happening more and more, like what I mentioned about sustainability drivers. Same thing, these are all the changing conditions that are happening more and more, and we cannot sit tight and do nothing. So we have to act on these things. So that's where considering the resiliency becomes important. The quantifying the resiliency is also important. As I said, like, you cannot just say that, my system is resilient and go with it, but, show me how resilient your system is. So the resiliency is all about, you have designed certain things and it's performing, but if unexpected event happens, you're going to compromise the performance. So you're going to disrupt the system, and then that disrupt system may exist for a while, and then you may be doing some adaptation, or the system itself could be adapting and then recovering the performance, and maybe reaching a stable recovery state, which may not be the same as the original state, but at least, a acceptable state to continue on. So this, basically we call it technical resiliency. And this can be calculated through engineering analysis, modeling, a lot of, advanced modeling can be done to look at how much is this performance loss, how long it's going to take, how long it's going to be in disrupted state, and how long it's going to take a recovery, and what will be the recovery state. So all these things could be calculated through engineering analysis, and then see how the technical resiliency is. And if the system that you have is not resilient, for example, if the loss is so much that you have a catastrophe, then you have to do something to the system, to evaluate some adapting strategies, so that you have this resiliency. Resiliency is all about recovering back to some acceptable performance conditions. So again, both the sustainability and resiliency are important because of again, changing conditions that are happening in the short term, and we need to look at the long-term survivability, that is sustainability. Now, so hopefully you understood what these two terms mean, sustainability and resiliency. Now let's get into the infrastructure. So when you talk about civil infrastructure, ASCE groups all the civil infrastructure into these almost like 17 different categories, right? And as a civil engineer, you may be specialist in environmental or structures or transportation, whatever, geotechnical. So you will be working in, all these kind of projects. And then in the US, ASCE rates the infrastructure, gives the score, and grades are given in this one also. This is 2021. I think the next one is coming up next year. So these are the grades. The US infrastructure is pretty old. It has been built long time ago, and a lot of these things need repairs or reconstruction. So that's why, the infrastructure rating is grades are very low. So if you are retrofitting or building a new one, what is important is to consider the sustainability and resiliency and smart, using all the advanced, technologies. And the geo-environmental engineering can be applied in this effort. So that's my, presentation goal is to show how geo-environmental engineering can help in making the infrastructure sustainable and resilient. I don't know this. You can see that there's somebody marked. Can you clear this one? Somebody has to clear that. You can see in the presentations. I don't know if you guys can see it or not.
Yeah, we see it.
You can see.
So can you clear that one? I think there is a way to clear that. Go into the tools, I think. Because that's going to be there in every slide that I'm going to show. Should I do it? Let me see. Okay, here. Clear this one. Somebody did something.
I think only host can remove itself.
Okay, who's the host? I am the host.
Yes, sir.
Okay, let me see. Okay, let's do this one, but let's go in the whole.
So again, you can share, sir.
Yeah. Tell me if you can see it or not.
Yes, sir.
Now it's good. We don't see anything.
Okay. So you're seeing only one screen, right? So, okay.
Yes.
So now let's look at this. Sustainable and resilient infrastructure. So I talked about sustainability and I talked about resiliency. And we should think about you cannot have a sustainability without resilience, right? So tomorrow you have extreme flooding and then your structure is not going to be, withstanding, it fails, then what is the point in looking at the long-term sustainability? It's going to collapse tomorrow under this extreme climate impact. So sustainability without resilience does not make sense. And the resiliency without sustainability also does not make sense because, if you want to make a resilient, and you want to use all the, fancy materials that have high carbon footprint, then you're going to have a lot of greenhouse gas emissions. So you're not really, addressing the root cause of the climate change. So you have to consider both of them, resiliency and sustainability, so that your systems are safe under the changing conditions that are happening now, and also you are addressing the future conditions. You want to look at the sustainable future. So that's why some people, use only sustainability, some people use only resiliency, but it is very important because these two terms are quite different, and you need to make sure that you use both of them together, because that shows that you are addressing the changing conditions, in near future, and also you are looking at long term, like future generations from the sustainability perspective. So what can you do to make infrastructure sustainable and resilient? So what kind of things? So you're a civil engineer, or you're going to design all these systems. What are the things that you should look for if I want to make the infrastructure sustainable and resilient? First thing is you need to have a low environmental impact, minimize the emissions, resource extractions, ecological disturbance. And you need to look at energy efficiency systems. You don't want to use a lot of energy. More energy means, more greenhouse gases and more environmental constraints. And you also want to look at the materials sustainability. So you cannot use the same materials that you have been using that it really cause the problems that we have. So we need to look at, sustainable materials. We need to be looking at the biodiversity protection and resilience to extreme events. This is what not in the codes right now. If you just say that I want to follow the codes that that are there for the design, then you will not be able to address these things. So these goes beyond the codes, and as a professional ethics, you must consider these things. And you need to have consider the low cascading impacts, because whatever resilient technical design you make it, that will have implications on environmental, social, and economic. So you need to make sure that those are not sidetracked. And you need to look at what are the social benefit of doing your infrastructure in the first place, and what are the social benefits by doing it in different ways. Okay. So that's important to consider. And bottom line is always cost. You don't want to spend more than what you should be doing. So a lot of times there is a misconception that sustainable designs are going to be more expensive, but actually, it is opposite. 'Cause sustainable designs are going to be more economical compared to the standard systems. So this is all about sustainability and resiliency. If you're not familiar with all these concepts, I highly recommend you to, look at this book. It should give you the information about sustainable engineering. Now let's come to the second part. So geo-environmental engineering. So we looked at sustainable and resilient infrastructure. And now, in order to achieve that one, I said like a geo-environment engineering could play a role. And the question is, what is geo-environmental engineering? So a lot of people don't have much idea about it, this one, but basically it is, broader field than our typical specializations that you see. So it is a multidisciplinary knowledge that you need to develop engineered solutions to geo-environmental problems. So the types of multidisciplinary knowledge that you are looking at is geotechnical engineering, environmental engineering, and then chemistry, biology, and contaminant transport, risk assessment, and some idea about environmental laws, environmental justice, environmental economics, and so forth. So, to come up with a holistic solution, engineered solution to a problem, it has to be multidisciplinary. So this is the field, the geoenvironmental engineering is combining this multidisciplinary knowledge to develop a holistic engineer solution. So, if you don't have this one, you may be, coming up with a solution to one component of your system. But, if you want to look at everything at the systems level holistically, then you need to combine this multidisciplinary background. So you can learn more about this geoenvironmental engineering from this article that I wrote, or you can, get hold of this book to understand the scope of geoenvironmental engineering. Now, I don't want to spend too much time on what is geoenvironmental engineering, but I want to give you some examples of how geoenvironmental engineering can be, used to develop sustainable and resilient infrastructure, right? So I gave you some examples here. So in terms of the construction materials, in terms of ground improvement, in terms of the foundations and earth retaining structures, in terms of the flood control, stormwater management, waste containment facilities, polluted land remediation. So I just taking these as examples. So what we do for, let's go through these examples very quickly. So see how geoenvironmental engineering can be applied to make infrastructure systems more sustainable and resilient. So here are the conventional construction materials, right? So mainly sand, aggregate, cement, and concrete and steel, right? But now it is well established that the resources for these materials is limited, and then we have a lot of improper waste management issues, and moreover, high carbon footprint and high environmental impacts, right? For example, manufacturing of the cement itself, could be a high environmental footprint, and then high cost of these materials. So there's a problem, right? So we cannot really have these conventional construction materials to be used continuously going into the future. So now, what are the options that we have, if we don't want to use those concrete and steel? And to be sustainable, we have all these industrial byproducts and recycled waste. Now, they are either improperly disposed, or they are disposed in landfills or some kind of disposal facilities. But these are not bad materials, So I just I'm showing you the pictures of some of the industrial byproducts and recycled materials that we tested in my lab, right? So these are all, good materials if you can use them properly. So there are a lot of uses of these materials. Just as an example, so you can make the concrete blocks, fly ash bricks, and in lieu of river sand, you could use a coal mine overburden sand, and there are many more construction materials that could be created from these recycled materials and waste materials. And then, any material that you can take it, you can do the sustainability assessment. For example, if you do the life cycle assessment, we did this one for, natural aggregate versus, aggregate created from the coal mine overburden. So you can see that, the environmental footprint of these alternative materials is much, much lower. So, if you can demonstrate that the material can perform technically as equivalent to our conventional material, and this kind of analysis clearly shows that this approach is much, much more sustainable in terms of the environmental footprint. So there are a lot of other materials being developed using these industrial byproducts, waste, soils, and their combinations. We call it composite materials. So geopolymer composites, recycled plastic soil composites, waste glass polymer composites, biochar soil composites, clay polymer, there's so many of them. So this last one, chitosan biochar bentonite composite that we are working on in our lab in a current project that we have. So basically you are looking at the industrial byproducts or waste and mixing with other wastes or some soil systems and creating these, new materials that have unique properties, and they can perform probably better than your conventional materials that you have. So that is the example. So in terms of how geo-environmental engineering comes in picture when you're looking at these materials. First of all, you're talking about industrial byproducts, waste materials and all those things. One of the concerns is, the toxicity, leachability of any contaminated, contaminants like metals or organics or whatever. So that can be, done. So in geo-environmental engineering field, we learn about leachability tests and doing the chemical analysis based on that. And then all these materials, and then even when you combine them, they're not soils, right? So these composites are going to be quite different in terms of their physical, chemical, thermal, biological, and geotechnical properties. And then to understand, those properties, you need to go into the mechanisms and the detailed characterization. That's where you need a little bit of, advanced chemistry, biology, and, more of, micro characterization, mineralogical characterizations, and so forth. So that's more than, the typical things you learn in typical geotechnical courses or in civil engineering courses in general. Durability becomes a big issue for these things, and field applications becomes important. Resiliency, changing climate and weather conditions, like, changing the moisture content, changing the pH, changing, temperature, these are the things that we conventionally don't look at it. And these becomes important in geo-environmental perspective. And the sustainability, how do you calculate the carbon footprint? How do you calculate the environmental impacts? How do I, calculate the social, economic benefits? So all this comes from, the geo-environmental engineering perspective. So yeah, so if you are looking for alternative construction materials using the industrial byproducts or waste materials, yeah, geo-environmental engineering can become handy to evaluate those materials and use of those. The ground improvement, right? So, you probably taken a course on ground improvement in undergraduate or graduate level in geotechnical engineering. So you talk about all these different soil improvement methods, right? And some of them, maybe deep soil mixing, grouting and all those things. And most of them, they use cement or lime. So if you look at all these conventional ground improvement methods, they're all resource intensive, right? And the energy intensive. And they have high carbon footprint, high environmental footprint, and durability is an issue, resiliency is an issue. So these are the problems that are making us think differently than these conventional methods. Then what are the what are the unconventional methods? What are the methods that we should be looking at it? Instead of cement and lime, we should be looking at alternative materials like, fly ash or, any other byproducts that you think could substitute for cement and lime. So if you can substitute cement or lime, then you are actually, having a lot of benefits in terms of low carbon footprint and, more in general, environmental footprint. So, or using the natural fibers, right, for soil reinforcement. Again, these are the natural materials, and they're manufacturing. You're not manufacturing them, so the environmental footprint is going to be much, much, much lower. And natural fibers and geosynthetics, that can be also can be an alternative. And if you have issues dealing with frost heaving, or if you want to have infiltration issues or erosion issues, you can look at alternatives compared to the conventional ground improvement methods, organosilane, or some of the chemicals that are people are using it. And then people are going into bio-based methods for ground improvement. This MICP and EICP, microbial induced carbon precipitation techniques, and a lot of papers that you see on these things. Basically, if you have cement, you can solidify that one by formation of calcium carbonates. And as a result, liquefaction resistance is going to be increased, and the strength is going to be increased, and so forth. So, instead of adding cement here, but you're, using the biological processes to cement the sand. And you could do it in the surface for erosion reduction. So this is again not a conventional method. It's an unconventional method, and you can use the different types of approaches, biological approaches to for erosion or soil stabilization. And instead of microbes, you can look at the plants to stabilize the slopes. It is called phytostabilization. And the plant's roots can help increase the shear strength, and then slopes can be much more stable. And then to make these plants grow, so you may have to do some organic amendment using compost or biochar or something like that. So you can see these are not conventional way of stabilizing the slopes, rather using the plants to stabilize. So this is again, more sustainable, and these are also resilient to changing conditions. The other one, not a conventional method, is electrokinetic stabilization, where you apply, small electric potential, and then, you can dewater and increase the strength of clay type soils. Again, this is again, you need a small power, DC power. It could be provided by solar energy. So, it's a very simple compared to the conventional methods, and it has all kinds of sustainability and resiliency benefits. So in the ground improvement methods, if you are, if you want to use anything other than the conventional methods, you need to have some good understanding of the geo-environmental issues. So I'm listing all those things, right? So you need to understand the processes, fundamental processes. If you are basing with some chemical or basing with biological or electrical or plants, you need to have that understanding of the couple processes that are leading to the final result of your soil stabilization, right? So that again is beyond traditional geotechnical engineering. And you need to look at the effect on subsurface, effect of surrounding environment. And in all these things, you need to look at any kind of unintended negative impacts, and what is the long-term durability, what is the resiliency, and what are the broader sustainability implications of all these things. So a lot of geo-environmental engineering issues needs to be addressed when you shift your approaches from conventional to some of these new and emerging techniques. Foundations and earth retaining structures, again, you have all these conventional foundation systems, but many of them, just like other conventional infrastructure systems, you are using a lot of steel, concrete, so they're not environmentally sustainable because of high carbon footprint. And there's a lot of retaining structures. Again, you use the concrete and steel. Again, they are resource intensive and high carbon footprint. So now, to avoid those things, to make the systems more sustainable and resilient also. So the nature-inspired solutions are being considered. A lot of research is going on in terms of alternative foundations, alternative retaining systems. For example, energy foundations is one approach where they are trying to harvest geothermal energy using the foundation systems. And instead of conventional, reinforced concrete or steel sheet pile walls, now, there are ways to use, waste materials, um, and, create these alternate retaining wall systems. So again, you are utilizing the waste materials, as a result, reducing the waste, and then you are creating these systems, and they are more sustainable and also more resilient for changing conditions. So again, you are going away from the traditional systems, so you need to have these geo-environmental issues to be addressed, right? So, and in terms of flood control and stormwater management, so for the flood control, we use all these traditional civil engineering systems, but they are not resilient to changing climate, weather conditions, high carbon footprint, high environmental footprint, and they are expensive. Now, as alternative, so for levees, especially, there's a lot of work on levees. Levees are basically these barriers in different forms. They are, aimed at protecting the nearby infrastructure and communities, especially, when you have rivers, streams, or coastal areas. And a lot of interesting work is going on. Recently, we did some work on how make existing levees more resilient to changing conditions. For example, if you have a high storm, water levels are more than what you expected in your previous designs. So if you do the stability analysis, you could have a slope stability problems or, piping problems. How do you fix those things? So, in our case study, we actually used a slag as a filter material, and, try to address the potential piping failure issue. So likewise, a lot of people are using geonaturals for slope stabilization of these levees. And then in some cases, they want to avoid using these levee systems. So they are creating these floodable parks. So if you have a coastal area, you don't want to have any permanent infrastructure. Rather, you want to have a park. And if there is no issue, then the park can be a beautiful place for people to go and enjoy. But if there is extreme storm, if there's a flood event, then park gets flooded, but that's okay. People are going to go home. There is no permanent infrastructure that to get it damaged. So and then when it recedes, then you don't have any problem. So like that, a lot of coastal areas, rather than putting a levee or flood wall, they are constructing these floodable parks. Again, this is the infrastructure that makes it sustainable and resilient, right? So if you had a levee, then you would be worried about the damage to that one. So there are a lot of geo-environmental issues associated with these systems. Anytime you use a recycled materials or waste materials, all kinds of geo-environmental issues come into picture. So how would, the surroundings will be affected by using these alternative systems, and the plants and trees, the floodable parks. This is kind of a new concept to civil engineers. How do we address those things? And then how do we say that these are sustainable, but, we need to quantify these impacts and see how sustainable those are. So civil engineers work on stormwater systems, basically sewer system, right? You have a network of manholes and pipes and like the discharge into rivers or detention ponds. But those kind of systems are considered to be inadequate or not sustainable. All right, so not resilient, not sustainable. So now this green infrastructure is being promoted, and a lot of geotechnical engineers, civil engineers are involved in designing of these things. So it could be bioswales, a rain garden or permeable pavements or green roofs. So these are all kind of a nice systems where you're allowing the infiltration of the rainwater that could have benefit the groundwater recharge, and you're not creating the stormwater. And then one of the problems is the stormwater could be contaminated, and creating a filter within these systems is extremely important. So you want to remove the contamination before you infiltrate the water into the surroundings. A lot of waste materials are being used to create permeable concrete pavements, and a lot of organic materials are used in in green roofs. So a lot of interesting things that are going on. And if you look at the communities, you could have these stormwater retention ponds like this. But in the past, this water used to be clean. But now with a runoff, passing through all the roadways, dirty roads and everything else, the water is contaminated. Now we are looking at, how do we put a liner systems in the bottom? So we are, looking at a project where, what kind of a liner system that we need to put for these retention ponds, so that the contamination does not infiltrate into the groundwater and cause the groundwater contamination. So all kinds of geo-environmental issues, whenever recycled materials, leachability, how it affects the surrounding environment, how the plant species could be affected, and looking at the broader sustainability impacts. So, so if you are thinking about these alternative systems, so we need to look at all these geo-environmental issues, and then, make sure that these systems don't cause any, adverse impacts. So it's important to look at these systems from fundamental perspectives. So, waste containment systems, these are landfills. These are engineered systems, and mainly, to prevent the soil and groundwater pollution. And a lot of materials are being used in the construction of liners and the cover systems. And, if you have a liquid waste, these are called surface impoundments, the construction of these, and a lot of innovative liner systems are being proposed for this one. And every time you dispose the waste, every day you have to put a daily cover. There are a lot of different alternatives coming for use of a cover. And as I mentioned, a lot of different types of liner systems using combination of different industrial byproducts. Better than the conventional liner systems or cover systems. And if you have a waste that degrades, and you're going to get gases, and again, these gases are greenhouse gases, and how do you control that one? So you can create these biogeochemical cover systems so that the gases are trapped. And then these landfills, as I told you, they produce the gas, and the gas could be collected, and you could create energy out of it. And again, if you're not getting enough gas, this system called leach recirculation to accelerate the degradation and get a substantial amount of gas that could be converted into energy. And we did a study, this kind of approach can really lead to both sustainability and resiliency. So when you're dealing with waste containment systems, there are all kinds of geo-environmental issues dealing with these kind of systems. Lastly, polluted land remediation and revitalization. If a site is contaminated like this one, you cannot really use this site for any purpose. In US, we have environmental laws that require the responsible party to clean up these kind of sites. And if you can clean up these sites, they can be used for some beneficial purpose. And how do you clean up? There are a lot of different ways to clean up. All those things are studied in geo-environmental engineering. You could have a waste containment systems where you can put this like kind of a slurry wall type things where contamination is not allowed to migrate, more than where it is now, and manage that contamination. And then, you can develop the site simultaneously. There are a lot of technologies that to clean up soil and groundwater. Again, those are all needs to be engineered, and the geo-environmental aspects, looking at the soil, looking at the chemistry, looking at the biology, hydrogeology, those all come into play. And, to make these systems more sustainable and resilient. You have a bioremediation, phytoremediation, again, very fascinating ways to clean up the soils and groundwater. Um, and they are much more sustainable and resilient compared to traditional physico-chemical methods that we have. So the whole idea is you don't want that land to be idle and the pollution to be causing the problems to humans, surrounding humans, and the environment. So if you clean up, you can build something on that one, and it will lead to a lot of socio-economic benefits. So that's all, the final goal is to, sustainable development. All right. So, so those are all the examples. I could go on into giving more details, but my whole idea was to explain first what is sustainability and what is resiliency, what is sustainable and resilient infrastructure is, and what kind of things we should be looking in the design of those systems. And then I was giving you some examples of, what kind of things that you could consider in your infrastructure design to make those sustainable and resilient. And then I was telling you that, in all these such projects, some geo-environmental aspects becomes important. Chemistry, biology, soil interactions becomes very important. And the geo-environmental engineering that way comes to very good use in developing these systems. So just the closing, we are having population growth, waste generation is increasing, resources are depleting, climate change is happening, and we cannot, have a status quo and go with whatever we have been doing. So we really need sustainable and resilient infrastructure. And one thing that I want to mention is, don't let people use these as buzzwords and sell the same old stuff. You need to emphasize having them calculate the sustainability and resiliency to demonstrate they are really sustainable and really resilient. So that's where, these frameworks and methodologies become very important. And as I mentioned, in looking at this alternative infrastructure systems, you will be using different materials, different approaches, more based on the nature. And in those scenarios, geo-environmental engineering, becomes very important. And all these systems, in general, they lead to sustainable and resilient infrastructure. So using nature-based waste and recycled materials in infrastructure systems will definitely help towards the sustainability and, and infrastructure. If you based on the nature-based, they're more resilient to conventional systems. So there are a lot of research opportunities, any field that you're looking in civil engineering, geo-environmental engineering or geotechnical or water resources, transportation. So just thinking about this sustainable and resilient infrastructure is a very broad field that all civil engineers can contribute. So hopefully, my presentation gave you some ideas on what is important, and you have taken away some lessons for your teaching classes, or even doing research, or if you are in a consulting business, hopefully you got a idea on looking at the projects through additional design criteria of sustainability and resiliency. Okay, thank you very much. And I don't know if I have time. I think I have some time, so I will be happy to answer any questions that you guys have.
Hello, dear participant. Are there anyone having doubts? If you have, please unmute yourself and ask.
Hello, sir. It was a very good presentation. I really liked what you said. Sir, I had one doubt. Like when you talked about that leachability test, what are, I'm trying to do some of these things for my BTech level, like undergraduate level projects. So what are some of the tests we can try to, check leachability at like undergraduate level? Is there any tests we can do to check, at a basic level?
Yeah, I mean, there are the UACPA methods. That one is called, TCLP method, toxicity characteristic leaching procedure. Then there is SPLP method. There are different, if you look at my Geo-environmental engineering book, it shows you, different leaching testing procedures. Some of them are a bit more complicated, some of them are simple. So essentially, it involves taking the material, passing a selected liquid, and then collecting that liquid and then analyzing for the chemicals of interest and see if any of those are which were not there before and they are present after passing through the material. So one of the challenging things, in doing all these leaching experiments is that you should have some way to analyze those chemicals of your interest. For example, if I'm using, if I'm interested in metals or lead, for example, is a can lead leach from this material? Then you need to be having a capability of analyzing, lead. So, if you're not capable of analyzing in your lab, just reach out to chemistry lab or chemical engineering lab or environmental engineering lab and see, what their capabilities are. So basically you can do the leaching test, but ultimately, you need to have somebody to analyze that liquid for chemicals of your interest. And look at that book that I have given you. So sometimes, it's important to select the method. Um, you know, uh, for example, if you are just looking at outdoor environment, just the rainwater infiltration, that's different. Sometimes you want to see if the material could be characterized as hazardous, then you should have to follow like a different leaching procedure. So my advice to you is, look at the references. There are different leaching procedures for different types of purposes, and then pick the one that fits your needs. And then what I found the most challenging part is to, have a capability to analyze the liquid samples that comes out of this testing.
Okay, thank you very much, sir. Yeah, I was actually trying to work with iron ore tailings and use them as like partial replacement in soil.
Mm-hmm.
I did some work, and yeah, now I was interested in seeing if there's any effect of like these trace earth metals or rare earth metals which might be leaching into the soil and contaminating the groundwater, something of this nature. So
Exactly. It's so important. I mean, so I see a lot of studies, they look at, the waste materials and they do testing for mechanical properties and other things, but they don't look at this leachability aspect. That's very important, when you are looking at any waste materials or recycled materials. So it's important. You don't want to use them and cause the spreading of the contamination all over. One thing I want to mention is, let's say you are using the tailings or whatever, that may have leachability issues. You can test that one. But when you mix with something, let's say you're mixing with soil or something else, so test under that mixed conditions also, because you know, the chemistry changes when you add two materials. So, and ultimate goal is what is your final material that you're creating, and look at the leachability of that final material. So, individually, some materials may leach, but when you combine all of them together, the way you want it to be used in the field, and if they don't leach, then you're safe.
Right. Thank you, sir. Thank you very much.
Hello, sir. This is Shaikh, coordinator of this FDP.
Hello, sir.
First of all, sir, I'm sorry if I did some mistake to communicate you. Maybe you may feel bad, so excuse me, sir. I apologize.
No issue. No issue. Yeah. Yeah.
Because,
No.
sir, currently I'm having some health issue.
Yeah.
Recently, I got a brain stroke due to my high BP. So mostly I'm avoiding talking during session. But still, I have a little question, a small question. Like for geotechnical investigation, we investigate some soil parameter like cohesion, C5, internal angle of internal friction, and then liquid limit, plastic limit, those things, permeability. So those geotechnical parameters we investigate. So are there any specific soil parameters which are important for geo-environmental problem solving or understanding?
No, I mean, the same things are important. For example, if you are constructing a, let's say a berm, or if you have a slope, so, you are using alternative materials, but fundamentally, you are doing all those things to improve the properties, geotechnical properties that you are interested in. So the methodology, analysis methodologies would be the same, because, if you are using soil, you have tested the soil, right?
Yes.
And you got the CNF, whatever shear strength parameters that you got it. But then if you are using the waste materials, so you really need to test the same way, but you need to again ask a question, is the conventional way of testing the soil and testing this waste material makes sense or not? Do you need to have like a special testing equipment, a special testing procedure to test this material, because it's not, typical soil? And but you're really aiming to get the shear strength parameters so that you can put those in your analysis and then get the results.
And what
So
about, sir, that what
yeah,
about that CEC value? Cation
what is it?
exchange capacity, CEC, cation exchange capacity.
Yeah. So
And so
that's those are all the things that are needed to understand, let's say, you to understand the mechanisms, right? So let's say you have the soil, and you amended with polymer, right? And then now you tested it, you got higher strength, right? Sometimes you could have a lower strength, so that's, you're not going to go for that one. If you have higher strength, what are the mechanisms why it caused that higher strength? So to understand that one, you need these fundamental properties, like cation exchange capacity, then
organic content.
you need a surface area, you
Yes.
need a surface charge, you need pH. So
Yes.
all this, in
Chemical
geotechnical
property.
engineering, we only talk about mechanical properties, hydraulic properties, but you need to know the chemical properties, what is the pH and other things. Then you can understand what the mechanisms that cause this, material to give you higher strength than, soil alone. So, and that understanding is very important, and then you want to also know whether that strength is, durable. Can you maintain that one? So sometimes you may have a situation where you increase the strength in the short term, but in the long term, because of whatever chemical, biological activity, it may go away, right? You don't want that one to happen. So, you want permanence, durability. So those kind of issues you can understand by having the fundamental, the soil chemistry, soil biology, actually, combination of chemistry and biology with the soil, right? So that's very important in dealing with this different scenarios, right? So whatever
sir.
you do in geotechnical engineering, in terms of the testing, in terms of the analysis, same things can be applied to this alternative. We're talking about alternative materials, alternative, methodologies or technologies. So I tell people that, whatever you're using, all the things you learn in geotechnical engineering can be applied in geo-environmental engineering or, sustainable and resilient engineering. But much more, you need to get in more stuff in there.
Thank you, sir. I understood. And thank you also for sharing with me those very free study material which you shared with me recently, 2 days back. It is so useful and important for me. I got so much benefited. Thank you, sir. Thank you.
Thank you so much. Yeah.
Are there anyone having some doubt? Dear participant?
Good evening, sir.
Yes.
Yeah. Go ahead.
Your voice is not on. Your voice is breaking.
Anamika, your voice is breaking. You don't have good connection, maybe.
General, let her put the query in the chat box.
Okay.
She can put her query in the chat box.
Anamika,
Anamika,
you can
hello.
put.
Yes, you're.
Only nitric acid. Yes, yes, yes.
Now it is clear. You please ask.
Hello.
Yeah.
For strong acid digestion test, can we use sulfuric acid instead of nitric acid?
Which test?
A strong acid digestion test for leaching, leachability.
Oh, this, you have to look at the procedures. So there's that acid digestion procedure is used for determining the total content of the metals in the soil. So you need to, again, look at my geoenvironmental engineering book. In that, I mentioned about the methods to extract or to, analyze the total metals and leachable metals. So you could use, depending upon the method, depending upon, so the whole idea of, sulfuric acid or nitric acid, both of them are acids you could use, but I think it's better off looking at any standard procedure and then following that rather than, making your own decision, because people, while developing the procedure, they looked at all the, issues associated with using either chemicals. So I would strongly recommend you to look at any standard procedure for acid digestion. That's called acid digestion procedure. And follow that. And, that the method could be more elaborate rather than just adding the acid. Sometimes you add the acid and then you heat it up and you add some oxidant to oxidize the organics. So there is, depending upon what you are trying to do. If you are trying to determine the total concentrations of metals in your soil, then you follow this acid digestion procedure. But if you are interested in leaching of metals from the soil, in a typical scenario, you don't use the acid. I mean, in a real situation, you don't have acid, right, passing through your material. So, or people use like a very dilute acetic acid to represent some conditions that could exist in the nature. So try to mimic, field conditions for leachability, okay? Because, if you do the leaching test with sulfuric acid and nitric acid, that does not simulate any field scenario. But if you are interested in knowing how much is the total content in the soil, yeah, that's fine. Okay.
Thank you, sir.
Is there anyone having doubts?
Hello.
Yeah.
Yes, please.
Good evening, sir.
Good evening.
Sir, I have doubt in regarding concrete material. Can we go for steel slag as an alternative material in place of aggregate? Because there is a lot of reaction mechanism, hydration mechanism due to presence of water. So there will be any risk of corrosion. So can we use as an alternative material in place of natural aggregate by steel slag?
Yeah, and you can look at it. You can look at the literature on there's so much literature on alternative concretes, right? So the whole idea is to first of all reduce the cement that you have in there, and also look for alternative fine aggregate and alternative coarse aggregate. So I don't do research on concrete. My colleague in my department does it, and he is trying out all the alternative materials as a fine aggregate and coarse aggregate, and the combinations of them. So I would recommend you to, again, what kind of steel slag you're looking at it. It also depends, right? And I would say, people are using it, and I want you to look at the literature and see what is the current status, and if anybody has looked at corrosion potential. Okay.
Okay. Thank you, sir. Yes.
But that's a good question. Good question, though. Like when you look at it, like a lot of steel plants generate the steel slag. So
Yes.
if you can utilize that one in concrete, you can consume a lot of it, and
Yeah.
save the aggregate, and also you don't have to dispose this slag as a waste material.
Yes, yes. Because a lot of research already going on in place of natural aggregate by steel slag. But
Yeah.
what about its feasibility? Because it is also important to do, is it feasible or not? Only there it is not important to use and replace the material. We have to think about its durability.
Yeah, exactly. That's all these studies, they basically do the same thing, right? Just you look at the material, and different percentages, and then do short term and then a long term durability under different conditions.
Okay, thank you so much.
Let us stop here. Actually, next session is nearing. Sir, for next year, I am booking you in advance. So again, we will do similar FDP. And next year also you want to, sir.
Sure.
Sir, we
So-
also sincerely appreciate the time and efforts to be
Yes,
with
sir.
us today, and we look forward to future interaction and collaboration. Thank you very much once again, sir.
And in
thank you.
future, sir,
Have a
our
good
approach
day,
will be nicer, sir. Our approach will be good because this is my
Okay.
first MDP.
Thank you so much.
Okay.
Yeah.
Thank you, sir.
Thank you, sir. Krishna Reddy, sir, thank you very much.
Yeah. Thank you so much, everyone.
Thank you, sir.
Bye, everyone.
Have a good day.
Okay. All right. Bye, everyone.
Bye.
Bye, sir.